Hello, beautiful humans. Just give me 1 second to get this set up. Weird craziness going on. Here we go. All right. So what I'm going to talk to you about today is that multiplicity business that we touched on last week. So how can we identify multiplicity in a graph or an equation that's already in factored form for us? Later this week, we're going to talk about how we can actually factor polynomials, and so we'll be using that going forward even when we have standard form. But for now, just with factored form. Okay, so this is the same definition of multiplicity that we had last week. It means that a factor is being counted more than once. So the actual factor is either a locator point or a vertex of like a mini quadratic or a mini cubic function. That root is actually landing on the axis. So even though it's only one intercept, it's counting for more than one root. So again, when we talk about the degree indicating the maximum number of roots, these multiplicities factor into that. Okay, so when you're given factored form, you're looking at anything that has an exponent value, like that guy there. So this has 1, 2, 3 real roots. X equals -7 has a multiplicity of 3. That root is counting 3 times. It's going to look like a little mini cubic function at x equals -7. So remember, inverse of zero product property is actually showing us what those roots are. So we're going to go to -7, 1, 2, 3, 4, 5, 6, 7. If we were to draw this, that little section there would be a little mini cubic function, and the locator point would be right on that intercept. Again, I didn't check for leading coefficient or anything on that to make sure it goes that way. It could, of course, also be going that way. So either would work as a cubic or as a multiplicity of 3. Okay, so when we're given a graph like this, we're looking for any intercepts that don't look like they fully pass through. They might be a locator point or a vertex of some kind. So that's what we're looking for. All right, so when I look at this first one here, notice this just passes right through. So if we're reading this from left to right, we're decreasing. We decrease right through that intercept there. So that's just a single root. It counts for 1. So this would be x plus 3, and that's only going to count once because we passed right through it. Okay, right here, this should be indicating to you, oh my goodness, this looks like a mini cubic function. So this is the factor x equals -1. So the actual factor is going to be x plus 1, and it's going to count for 3. So we need to raise that to a power of 3, again, indicating that that's counting 3 separate times. And then over here, this looks like a little mini quadratic. Notice as we're reading left to right, we're decreasing. Oop, we hit the axis, and now we are increasing. So when you hit the vertex, or when you hit the x-axis, you are then changing, you're going from increasing to decreasing or decreasing to increasing. That is an indication that you have an even root, a multiplicity to an even power happening right there. So this is going to be x minus 2, and we're going to square it because it's a bounce point. It's counting as double. It looks like a little mini quadratic. So that's what we're going to be talking about more today. All right, so when we're looking for this, we're going to identify what the roots are if they have a multiplicity, and then we're going to give ourselves a little rough sketch of what this thing might look like. All right, so what are the roots? Well, we know the roots, we know the roots are going to be zero product property, right? So we're going to set each of these terms equal to 0 and solve for those roots. So x minus 3, if we were to set this equal to 0, we would add 3 on both sides, and we'd get that x equals 3. So this root is 3, this one's -2, and this is -7. Only one of these has a multiplicity, and of course it's -2, and it has a multiplicity of 2, because it's being raised to the power of 2. So that's a bounce point. All right, so let's, before we do a rough sketch, let's identify the leading coefficient. There's a 1 in front of this x, a 1 in front of this x, and a 1 in front of that x, meaning the leading coefficient's just going to be 1. Okay, so that's a positive leading coefficient, which means my right arm is going to face up, right arm up, because I have a positive leading coefficient. All right, what's the degree then? How many total x's would I have? 1 from here 2 from here because this is being raised to the power of 2. So that's 1, 2, 3, and then a total of 4. This is a degree 4 polynomial. So now I know that both arms are going to face up. That's a quadratic, of course, so that's not what that would look like. But a degree 4 polynomial will look something like this, and the arms will be up. So to give myself a rough sketch, all I need to do is plot my roots. So x equals 3, that's going to be a root. It's just a pass through because it has no multiplicity. X equals -2 is my double. This is a bounce point. So you might want to just indicate to yourself some way that is a double root. That's going to count twice, so it's going to be special when we graph it. And then -7, 1, 2, 3, 4, 5, 6, and 7 is also just a pass through. All right, so I know my arms are up, so I know that the pass throughs have to have arms ending up. And then I know I need a bounce point right there, so it's going to look something like that. Ding, ding, ding. And again, we don't know how deep these hills or valley, or how tall the hills are or deep the valleys are. We're just giving an approximate based on the information we know right now. So what am I looking for you to be able to do? Spot the actual roots. So you should actually plot where these things are crossing. And then of course you're looking for any multiplicity. All right, so you give this one a shot. So we have a x equals 0, and that has a multiplicity of 3 because of this term here. So when I do zero product property, if I just have x, that means x must be 0. We know that x equals -1, and that has a multiplicity of 2 because it's being raised to the second power. We also know that x equals +9 also has a multiplicity of 2. Again, it's being squared. All right, let's identify the leading coefficient. 1, 1, and 1. 1 times 1 times 1 is still 1. Let's identify the degree. We have 3 x's here, plus 2 more, 4, 5, plus 2 more, 3, 4, 5, 6, 7. Degree 7. So this is a degree 7. That means that, positive leading coefficient means my right arm is up. An odd degree means that my left arm is going to be down. So overall, after it does all its little curvy business, it's going to look something like that. So let's plot our roots, pay attention to our multiplicity, and give this a rough sketch. So at 0, we're going to have a little cubic. So this is going to be a degree 3. I'm just going to put little numbers at my roots to indicate what I'm doing here. At -1, I'm going to have a bounce point. That's a degree 2. And at +9, 1, 2, 3, 4, 5, 6, 7, 8, 9, I'm also going to have a bounce point, a degree 2. All right, this is my last root over here, and I know my arm needs to end up because I have a positive leading coefficient. I'm actually going to undo that because I passed through, and this one will not pass through because it's a bounce point. So if the right arm is ending up, I know this thing's going to come down, hit the bounce, boop, and end up. All right, so because it's a double root, it's bouncing. Okay, this next root that I'm going to pass through over here at 0 is a cubic. So I want it to look like a little mini cubic function, and I know it's going to be coming from over here. So it's going to look something like that, a little mini cubic. So now I'm just going to connect those. Again, we don't know exactly what this is going to look like. Of course, we're giving our best rough estimate. Okay, and then coming up, this thing's going to come up, hit this bounce point, and go right back down. So this is going to do something like that. And then your arrow will face down. Again, odd degree means right arm up, left arm down if you have positive leading coefficient, which we do. So again, they start to look kind of funky when we have multiple multiplicities. And again, this is a rough sketch. But yeah, there you go. Hopefully that's making sense. All right, I see no multiplicity on this, which means we have x equals 5, x equals 3, and x equals -6. Those are our roots. We have a leading coefficient again of 1, and this time our degree is just 3 because none of these are being raised to any powers. So we just have to plot our roots. 1, 2, 3, 4, 5. They're all going to just be pass-throughs, and then we just need to pay attention to what our degree is and if our arms are up or down. Okay, this is an odd degree and a positive leading coefficient, so I know my right arm is going to be facing up and my left arm is going to be facing down. So then we just go on through these. Whoops. That passes through there. Here, let me do a little better job. like that. Okay, so again, no multiplicity means these value or the graph is just going to pass right through, nothing to bounce or pay attention to that turning point of a cube root. All right, let's look at this one. X equals 9 has a multiplicity of 2. X equals 1 has a multiplicity of 2. And x equals -2 has a multiplicity of 3. 2, 4, 3 more is 7. This is a degree 7. Again, our leading coefficient is just 1. So we know our right arm is going to face up, and then we have all these multiplicities to deal with. All right, so at positive 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's a bounce point. And then, so bounce point, double, right? At x equals 1, and that's a double. And then at -2, we're going to have a cubic. Okay, so we know our right arm is facing up, and this is a bounce point. So this thing's going to bounce off like that, right arm up. We're then going to head over here where we have another bounce point. So it's going to hit, whoop. Oh, come on now. Okay, hit there. And then, okay, stop. And then we're going to come right back up, whoop. And then this guy is going to have a, oh, that's terrible. A locator point right there, right? That little cubic function. And then the arm is going to continue heading down because this is an odd degree polynomial. All right, one thing I do want to go back and point out, if we were to draw an imaginary x-intercept down here, notice we would have 1, 2, 3, possibly 4 real roots, which match, oops, go back, which matches our degree, right? So that matches there. Same thing here. This, remember, cubic functions, if we were to exaggerate their curves, look like that. So that could have 1, 2, 3, but this one only gets 1. So just pay attention to that. Remember that the hills and valleys thing can get confusing with multiplicity because they don't look as exaggerated as they could. Remember, a cubic function could be as exaggerated as that. Very clearly one hill, one valley. But again, this section right here, if you were to zoom in, you have like a little mini hill here and a mini valley there, right? But it's not exaggerated, it's just flattening there. So even though you can't really see the exaggerated hill and valley, it is counting for 3 possible roots. Okay, same thing here. There you have your exaggerated, so there are your 3 roots. Again, if we were to pass through up here, you'd see 1, 2, 3, 4. This is actually going to count as 3 right here, getting us all the way up to our 7 that matches our degree. All right, so how do we spot multiplicity from a graph? Well, now we're going to look for anything that looks like that bounce point or a cubic function, anything that's not just directly passing right through. So this right here appears to be a bounce point, so I would call that a multiplicity of 2. The other root that I have here is 0, and it's just passing right through. So we want to identify what the roots are, and it says to assume that we either have a positive a or a negative a, so just positive 1 or negative 1. So we don't have to solve for a here, but we do have to pay attention to what the arms are doing to decide if it's a positive or a negative a value. All right, so let's determine, and you know what, let's not call it a, let's call it our leading coefficient because that's better. Our leading coefficient here. Well, my right arm is facing down, so I know that my leading coefficient must be -1, given the options of positive or negative. So this right arm faces down, so that's a -1 leading coefficient. All right, if I want to determine the degree of this is 1 hill or 1 valley, 1 hill. Our degree is always 1 more than that. So I assume that my degree is degree 3. The other way you can check this, what would the maximum number of intercepts be if I were to draw my x-axis wherever I wanted it? We could have 3 possible intercepts. So again, a degree 3 polynomial. But this guy counts for 2 because it bounces right off that axis, right? It hits the axis, goes right back up. So we are decreasing, boom, we hit the axis. Now we are increasing, indicating you have some kind of multiplicity there. So we know that is at x equals, looks like -4 there. So x equals -4 means my factor is x plus 4, inverse of zero product property. And we know that needs to be squared. And then I also have just plain old x, right? If x equals 0, that's just x. So then we're also going to multiply this by x. and that is the possible equation to match our function. Again, we didn't plug in a value to determine for sure that our a value was -1, but they told you to assume that, so I'm confident it is. All right, and then you could say, of course, this is equal to f of x. Okay, all right, what about this one? Give this a shot, look for multiplicity, see if you can write it in factored form. All right, the only multiplicity I see is right there in the middle. That appears to bounce off, whereas over here we just pass right through. All right, so my factor is going to be x plus 4. That doesn't have any multiplicity. I'm just passing right through. And then I also have x. This is going to have a multiplicity because it bounces off. Boom, hits, comes right back down. So that appears to be a multiplicity of 2. Last but not least, x minus 6, again, just passing right through, so that does not have any multiplicity. Now let's double check that this is a degree 4 because we have 1, 2, 3, 4. So I believe I have a degree 4 polynomial. If I were again to draw my axis down here, I could have 1, 2, 3, potentially 4 real roots. So that appears to be a degree 4 polynomial, matches what I think. So this would be good. Again, typically we would write this as x squared times x plus 4 times x minus 6. Just descending order with the highest exponent value first would be the more normal way to write that. Again, my a value we didn't talk about, but it's going to be positive because our leading coefficient is going to be positive because the arms are facing up. With an even degree polynomial, if the arms are up, the leading coefficient must be positive. All right, let's give this one a shot, looking for, again, multiplicity here. Pass through. Ooh, this looks funky. This looks to be a cubic. Again, if I were to draw my little cubic function and I could exaggerate it, that's what looks to be happening right there. So we have x plus 7 is one of our factors. Again, has no multiplicity, passes right through, whoop, increasing, still increasing as we cross the x-axis. Same thing with our next factor, which is 0, decreasing, passing right through, still decreasing. So plain old x is just going to be by itself there. And then at x equals 8, which is the factor x minus 8, we see our little mini cubic function. So this appears to be cubed. Now we have a right arm facing up. So this appears to have a leading coefficient of positive 1. Again, this would typically be written with the x term by itself out in front, more like this. But either would be fine for now. All right, give this last one your best shot. All right, I see what appears to be a cubic function there. Again, if you were to think about it like that, cubic. I also see what appears to be a bounce point there. So that appears to be a square term there. And then this guy just passes right through. Okay, so at that was x equals -4. So that's x plus 4 appears to be a cubic root. And then at x plus 1, we appear to have a double root, a bounce point there. So square that. And then at just plain old x appears to pass through. Okay, let's check this out. We have both arms facing down, which means this should be an even degree, and the arms are facing down, so we need a negative leading coefficient. So I'm going to multiply this whole thing by -1 because I know my arms are down. Okay, this is 3 x's, 4, 5, and 6. So this is a degree 6 polynomial, which jives with the fact that it appears to be even on my graph. Again, this would probably typically be written as -x times x plus 2 squared times x, or the other way actually. Anyway, x plus 4 cubed, or you could write, that's actually increasing. So we're starting with an exponent of 1, 2, and then 3. Typically, we write it in descending order, opposite of that, but in factored form, it's not nearly as consistent. All right, hopefully that makes sense and gives you a better understanding of multiplicity. Have a wonderful rest of your day.